Welcome back to ICCP. It's my pleasure to introduce the third and final keynote of the conference. So far we've had two great keynotes on, mostly focusing on algorithms, cognitive science, and related topics. But now we're really fortunate to have Mark Itzler with us, giving a keynote on more on the optics and electronics of computational imaging. And Mark is the VP of LiDAR at Argo AI, which is one of the leading AI and autonomous driving companies, mainly working for Ford. Mark has extensive experience on semiconductor photodetector technology. He actually bridges academia and industry. He has over 100 papers in this space, mostly active in the IEEE and SPIA world, where he's also a fellow. But he also founded Princeton Lightwave, which was one of the leading companies doing single-photon LiDAR. So single-photon LiDAR uses single-photon detectors to really push the envelope of what LiDAR is capable of. And he was the CTO and CEO of Princeton Lightwave, which was later acquired by Argo. And they've been really pushing the envelope of shortwave, infrared, single-photon LiDAR systems. And he's going to tell us more about that for Airborne and Automotive applications. So we're really fortunate to have you here today, Mark, and thanks for coming.
Thank you very much, Gordon. Thanks for the introduction, and thanks to Ian and the rest of the organizers for the invitation to be here. I was just saying to Gordon and Ian that I'm sorry not to be able to meet everybody in person, but it's a pleasure to be able to present this material to you remotely. So as Gordon said, what I'm going to go through today is some work that I and my colleagues have been doing for the last decade or so, involving single-photon LiDAR imaging using Geiger mode avalanche photodiodes, and I'll tell you more about those detectors. And in particular, we've been at the very exciting transition from airborne to automotive platforms with that technology, and that's what I'd like to tell you more about today. So just as a brief outline of material I'll go through, after a short introduction, I'll first walk you through how a Geiger mode imaging camera is organized structurally. I'll go through its anatomy a little bit and give you a feel for what some of the elements are in there. And then I'll show you a number of applications that those cameras have enabled over the last half a dozen years or so in various kinds of time-of-flight imaging. A fair amount of it being airborne, but also some other interesting examples, some of which I think this community will be very familiar with. Then I'll talk a little bit about that transition of going from those airborne applications to using this technology on automotive platforms, and very specifically to enable autonomous vehicle operation. LiDAR is also being used in driver assistance functions, but as I'll explain, at Argo, we're focused really on the very high performance required for full autonomy. And then, seeing how much time I have, I'll go through some of the distinctions between this shortwave infrared Geiger mode technology and the previous approach is something I would refer to as kind of the legacy LiDAR, and I'll talk a little bit about how those are different. So just a quick introduction to Argo itself. As Gordon mentioned, Argo is one of the leading companies working on the development of fully autonomous vehicles. It was founded at the very end of 2016 and raised a significant amount of funding from Ford Motor Company in February of 2017. And they have been our primary automotive manufacturing partner up until now. In fact, last summer, Argo announced that they were getting an equal investment from Volkswagen, and that investment is set to close actually just in the next few weeks. And so we will have our second major automotive partner on board, working with us to deploy our full self-driving system, and this is something that most folks who are familiar with it recognize as being one of the most challenging applications of a number of different fields: computer science, robotics, artificial intelligence. But the sensors are absolutely critical to this system as well. Obviously, the software is an enormous focus for the company, but the hardware is certainly essential in enabling that full autonomy. And in particular, we are one of the majority, if not almost all, of the companies in this space that believe that LiDAR, using time of flight imaging, is an essential sensing technology to collect the kind of three-dimensional situational awareness that the vehicle needs in order to make decisions about how to operate and to be fully autonomous. And as I mentioned, we're focused on high performance that enables that full autonomy, not just functions that assist a human driver that will still remain in control of the car. Those have tremendous value, and there's a very interesting market for LiDAR in those driver assistance functions. That's just not where we happen to be focused. So to give you a little bit of background about how I and my colleagues developing LiDAR got to Argo, it was first a recognition that 3D sensing capability that LiDAR brings will be essential in autonomous vehicles. Argo uses many other sensing technologies that folks would be quite familiar with, certainly high-resolution cameras and video and radar, various acoustic technologies. Those are all things that are part of the sensor suite that helps the car collect information about the environment around it. But the LiDAR technology was something that was sufficiently new and immature that Argo felt strongly that was something that they wanted to have in-house so that we had a really good understanding of the technology, and to work on technology in LiDAR that would be focused out in the future, not just for deployment in current, less demanding situations. So Argo acquired Princeton Lightwave in October of 2017. Our focus up until that point really had been mostly on Geiger mode technology for airborne LiDAR applications. And so our flagship product was the camera that you see there on the left. I'm going to experiment with my pointer now. Here we go. And this camera was something that was a primary product for many customers that were integrating it into full LiDAR systems and then deploying on airborne platforms. Since the acquisition, our team working at Argo on LiDAR has now been focused solely on automotive applications. In fact, Argo sold the camera business to one of Princeton Lightwave's former customers, Ball Aerospace. They have continued to make those cameras available commercially, but at Argo, we have transitioned entirely to working just on automotive LiDAR. So just as kind of a quick summary, and I'll go through more of this in detail, this technology is fairly well proven in airborne applications. It's something that a number of customers have used for several years now. And it was a technology where we were developing the key hardware, all of the elements that go into making that camera for nearly a decade. And again, I'll talk more about that shortly. One other topic to address before I get into more of the details of the detector technology is, why would you want to detect shortwave infrared, or as I refer to it frequently in this talk, SWIR photons? Working at wavelengths beyond 1 micron have a number of benefits. We at Princeton Lightwave started working on single photon detectors initially actually for fiber optic communications applications, for single photon communications like quantum key distribution. And the incentive to work at these wavelengths for fiber optics is that the minimal loss in optical fiber is at a wavelength of about 1.5 microns. And that spurred a lot of the development of this technology going back at least 20 years with the advent of long-haul fiber optic communications. Another driver for working at these longer wavelengths is covertness. And this was actually an incentive for many of the organizations in the defense community. This wavelength is certainly not seen by human vision. It's also beyond the ability of image intensifier night vision goggles to see it. And so covertness was another factor that spurred the development of this technology. A third thing is that it is still reflective imaging. It is not a thermal imaging technology like detectors that work out at longer wavelengths and are based on much lower energy photons out at longer wavelengths. So the fact that it's reflective means that a lot of the intuition and processing that you can use in the visible domain remains quite relevant for doing this kind of imaging. Now, the fourth item there is probably the one that is the biggest factor in terms of why this technology has broad applicability and matters for the automotive space, and for that matter, any other LiDAR that's going to be deployed in commercial situations in the presence of people. There's significantly greater eye safety for working at wavelengths with active imaging beyond 1.4 microns. And so I'll say more about that later. There are environmental factors involving atmospheric attenuation and other technology factors, like the fact that many of these components have matured from their application to telecom. But the key thing to take away here is that in order to image in the shortwave infrared, we have to use a different material system, the so-called indium gallium arsenide phosphide compound semiconductor system, to see between 0.9 and 1.7 microns. There is a lot of work going on in silicon SPADs, and I really, or Geiger mode APDs. I won't say much about it at all today, but part of the reason that we have not focused on that is because they work only at shorter wavelengths, shorter than 1 micron. So let me move now into a little bit of an overview of the detector technology itself. The core device that we've been working with for many years now is referred to as an avalanche photodiode. I assume many, if not most of you, are familiar with these. Without getting into too much of the detail of the device design, the key to take away is that there really are two fundamental layers of the device. One is the semiconductor layer in which photons are absorbed, and what the composition of that material is will determine what wavelengths of light are absorbed by the detector and it can be sensitive to. And once the photons are absorbed and generate electrical carriers, those carriers are then multiplied in this multiplication region or avalanche region, which is what gives the device its name. And that creates gain that gives the detector more sensitivity than other kinds of semiconductor detectors that don't have this gain. I also want to point out that through most of this talk, I referred to Geiger mode avalanche photodiodes, or GMAPDs. These are exactly synonymous with single photon avalanche diodes, or SPADs. Many of you may be more familiar with that acronym. It's used very frequently by folks who work on these devices using silicon. So just to make a distinction between the sort of normal or legacy operation of an avalanche photodiode and the so-called Geiger mode, this is a current voltage characteristic. The details are not that important, but really the one takeaway here is that there is a critical voltage when an avalanche photodiode is biased at that voltage, where the response essentially becomes infinite. It goes into avalanche, and that avalanche can be self-sustaining, and the gain is essentially ill-defined at that point. It just diverges. What a linear mode avalanche photodiode does is it works below that so-called breakdown voltage. And it's called linear mode because the amount of photocurrent coming out of the device is simply linearly proportional to the amount of optical energy that comes into the device. And so it is very convenient for those and useful in those applications where you want analog detection as the key focus. Now, what we're using this device for is to detect single photons. And in this mode of operation, basically what you're doing is you're arming the Geiger mode APD above the breakdown voltage. It's basically in a metastable state now where the creation of a single electrical carrier can trigger an avalanche. That's what would cause this self-sustaining avalanche in the linear mode. But here, what we're doing is we're arming the device. We're waiting for a photon to arrive. When it does, we see an avalanche that essentially results in a macroscopic amount of current. And then we actively quench the device. Can be passively quenched, but there is a mechanism behind the detector that must quench the device so that it can go back into its quiescent state below breakdown and then be rearmed for the next detection. And the way to think about this device is really that it is more of a digital switch. The next slide kind of shows this a little more clearly. I can think of putting various amounts of optical input into the detector. I can have a strong pulse with thousands or tens of thousands or more of photons. I might have a weak pulse with only hundreds or maybe even dozens of photons. And then, of course, there are those situations where I want to detect just a single photon. Now, in a linear mode receiver, there's always electrical noise to contend with. And so the analog response from this avalanche photodiode detector needs to get above a certain detection threshold. This threshold would be set above the electrical noise. And so it does take some minimum number of photons arriving essentially simultaneously to trigger the linear mode avalanche photodiode. As a rule of thumb, it needs generally at least hundreds of photons in order to get a response above the detection threshold. And then above that point, the response is often analog. In the Geiger mode, that biasing above the breakdown and the macroscopic pulse of current that's caused by that avalanche breakdown essentially gives the same response regardless of how much optical energy comes into the device. So whether I have a big pulse or a weak pulse, or even just a single photon, I'm getting essentially the same digital response. And in some ways, it's more appropriate to think of it as almost more of a switch. Now, in this way, we can get down to the point where we can detect single photons with this detector. One drawback it does have is, as you'll see here, the response, which I've shown schematically, is essentially equivalent regardless of how many photons come in. So we don't actually get photon number resolution from this detector. And in order to get contrast when we're making measurements, we make multiple measurements, and I'll show a little bit more of that as we move along. So here's my basic detector. The goal of then putting these into cameras is to first integrate that structure into large format arrays. We get the benefit of semiconductor scaling. Although it's not a silicon device, it uses many of the same kinds of semiconductor fabrication, wafer scale fabrication processes for compound semiconductors that are used for silicon. And so here's a single pixel that then is integrated into, this was a first generation of array with 32 by 32 at 100 micron pitch. Seems pretty archaic in terms of having small pixel count and a very large pitch, but you have to think about this from the perspective that before, for LiDAR measurements, all that would have been available were single devices, single element detectors. And so now suddenly having 1,000 detectors in parallel was incredibly powerful. Taking that photodiode array, the goal was then to integrate it into a focal plane array. The detectors generally have a fairly low fill factor within each pixel area on their own, and so we use microlens arrays to collect light everywhere within the effective area, in this case of the 100 micron by 100 micron pixel area, collect that light, focus it down to just a single active region in the photodiode array. And then the other critical semiconductor chip that's in this focal plane array is the readout integrated circuit. This is a CMOS circuit that essentially is the brains of the focal plane. It controls all of the biasing of the devices, and it generates all of the timing information that comes out of this focal plane array. So within each pixel, there are counters that provide a timestamp for when an avalanche occurs at a given location, a given pixel in the array. And so these are photographs of the fully assembled unit that forms the focal plane That would then go into a camera. Our next generation device quickly halved the pitch, went up to 4 times the number of detectors in a 128 by 32 format. And so this was all integrated into a camera which was FPGA driven and had fairly robust performance in terms of user interfaces for people to use these quite flexibly in a lot of applications. And so just to go through now how that camera would be used in a time of flight imaging scenario, the camera itself would be synchronized to a pulsed laser. A delay could be introduced between the laser pulse and arming the camera itself. There are certain applications, for instance, like airborne applications, where there's no need for the camera to turn on when the laser pulse goes out. If I give a quick example here of a 6-kilometer altitude, you've got a 12-kilometer round trip distance. Basically, there's a 40 microsecond round trip time. And so it makes a lot of sense just to wait until you're expecting returns from the ground to turn the camera on. This camera, at its highest resolution time-wise, with the best timing quantization, it could run at a quarter of a nanosecond, which gives about 4 centimeter resolution on the range measurement. And by doing some averaging of these measurements, many users were able to get to centimeter scale accuracy. And one thing that we did with this camera is we were able to design it to run at extremely high frame rates. There aren't a lot of pixels. We could make a fast readout. And so the effective frame rate was almost 200 kilohertz. And that was very beneficial for doing the sorts of averaging that people wanted to do when they were doing photon counting type measurements. So let me move on now to some of the applications of the technology and what different groups around the world have done with SWIR, shortwave infrared Geiger mode time of flight imaging. Just want to start out by giving credit to the many scores of probably hundreds of people that have worked on this technology at MIT Lincoln Laboratory for probably the last 20 years at least. They really did a tremendous amount of seminal work that showed the potential for Geiger mode LiDAR imaging. And they were a unique organization to do so, right? In one entity, they had specialists in the materials technology and the device development, and they were able to make all these Geiger mode detectors right there at Lincoln, do the integration into higher level cameras and full LiDARs, and then put them onto aircraft right next door at Hanscom Air Force Base, where they share the facility. And so they really had a holistic view of how to develop the technology and made great use of those resources. These are data that came, one of the, I guess, earliest uses of a system that they had developed as a test bed was sent out to Haiti right after the 2010 earthquake. And they were looking to assess whether roadways were still going to be navigable there. And they showed that they could take imagery that would indicate whether damage to the roads was in fact a large hole or a pile of rubble. They could estimate the volume of what was in that rubble, so they knew what equipment was needed to clear it. It was one of the first times that this technology had been deployed to give this kind of information. Now, one of the companies that Princeton Lightwave worked with quite early on with the cameras was Harris Corporation. Harris has a very large geospatial imaging business, and they had used this camera to develop a LiDAR for commercial imaging. This is still an airborne application, but not a defense application. This is something where they took the 128 by 32 cameras and basically took those 4,000 detectors and created a LiDAR that had capability that in many ways was far exceeding the capability of the previous airborne mapping systems, which were based on a single laser detector pair, the so-called flying spot, scanning a single spot around to map out areas. And so what they have shown is that they have very, very high collection rates with this technology. It comes from two factors primarily. One, that they could deploy this camera with thousands of detectors and instead of a single detector. The other big advantage to the single photon sensitivity of these detectors is that they could fly at higher elevation and still be able to collect reflections from the ground. And because they were at higher elevation, they could scan much larger areas. So compared to previous technologies where maybe there was a swath width on the order of half a kilometer, they were scanning areas as wide as 5 kilometers in a single pass. And there's that kind of characteristic 10x improvement in what the technology was capable of compared to previous LiDARs. And so here's some of the kinds of imagery that they would collect. They would be taking data anywhere from probably 2 to 10 points per square meter. They were capable of going to even twice that, 20 points per square meter. And so just a few tens of centimeters was the capability of this. And that gave you the ability to have really beautiful high resolution data for customers that had a myriad applications, many reasons why they wanted this, everything from mapping cities or even county-wide areas for local governments to this is imagery from the McGuire Nuclear Station in North Carolina. They've published many images based on this technology, but it was these are beautiful results in terms of what they could do for very high altitude mapping. Another set of customers that Princeton Lightwave was involved with were those in defense organizations where there were a number of similar kinds of applications. In fact, object identification at very long range in targeting pods on the underside of defense aircraft over multiple kilometer ranges was a key focus for these cameras. Another customer, United Technologies Aerospace Systems, was working on a LiDAR system to be incorporated into an autonomous helicopter where the navigation was autonomous and used many sensors, including that LiDAR. This demo was up on YouTube at the end of 2015 using Sikorsky Blackhawks. Another application, again, another defense company, Leonardo. This is a division formerly known as Celex in the UK, actually in Scotland, right outside of Edinburgh, that was using the cameras to do long-range ground-based imaging. They were imaging out of their labs kind of across the city, looking at 9 kilometers with the 32 by 32 camera. They were working at 1.5 microns so that this could be an eye-safe implementation. And what they show here is through a telescope. Here's a visible image of the tree that they were imaging at a 9-kilometer distance. And what they found, in fact, that they didn't expect to see when they began this experiment was not only could they make out a lot of the detail of the tree canopy and resolution, again, down to just a few centimeters based on the timing capability of the camera, what they also found is that they could see through the foliage and actually map out the grade of the slope behind the tree. So in this scene, this was a really nice example of extremely long range foliage penetration. And that was the sort of capability that a single photon sensitive device could give. The imaging was extremely photon starved at these kinds of ranges and with a fairly modest pulse energy of 4 microjoules. And so this was a very nice result of what you could be doing even on the ground. Another airborne application that was extremely interesting was a bathymetric LiDAR. Grady Toole and his team at the Georgia Tech Research Institute had realized that, they were always using green lasers because that's the wavelength that best penetrates seawater so that they can map the sea floor or see objects under the sea surface. But when the sea was choppy and the surface of the sea had lots of angles that were distorting the beam, they would get beam steering effects that were really problematic. So they realized that they could take our camera, sensitive in this case, they worked with a version at 1064 nanometers, and working at that shortwave infrared wavelength, they could essentially co-align the green laser with the IR laser, and then the reflection of the IR light allowed them to map out the surface of the sea, and so they could get normal vectors for everywhere that the green was penetrating the water, and that allowed them to get much better accuracy in terms of understanding the return signal they were getting, because they now understood the exact topology of the sea surface that the green beam was going through. And then finally, this is the last example I'll show. This is one that many folks in this community are probably familiar with. This is work that Martin Lorenzis and his colleagues at ISL did several years ago. Just a beautiful experiment of non-line of sight imaging, but in shortwave infrared wavelengths. So using a Princeton lightwave camera, they were using a fiber laser at about 1.5 microns. Their laser was set up here with a camera set up to image a screen out at a few meters distance. And the laser beam was designed to go through that field of view of the camera, hit the screen outside the field of view of the camera, and then reflect off a non-line of sight target with reflections from this target hitting the screen, and then returns coming to the camera that could then be imaged. And so this plot here probably gives the clearest indication of a number of features that they saw. First of all, they saw first order reflections from the backscattering of the light going through the imaging field of view of the camera and giving this fairly weak signal here. The second, there was another first order reflection that involved the fact that the laser diffracted, although it was a fairly low divergence beam, there was still diffraction from the output optics that caused some very, very small amount of photon energy to reach the screen directly, and the reflection of that diffracted light could be seen here. Then the largest order reflection they were getting was actually second order. The laser beam hit the screen outside the field of view, was reflected along the surface of the screen, and then from somewhere within the imaging field of view of the camera, it was then reflected again and made its way back to the camera. That's this third peak here. And then finally, the non-line of sight third order effect is the reflection from the screen outside the field of view to the non-line of sight target, back to the screen that the camera was imaging, and to the camera. Now, they made these measurements with building up histograms of about 16,000 or so measurements. These reflections are down at about a 1% detection probability, and these are very, very weak signals coming back. So this is an experiment that I don't imagine could be done without single photon sensitivity, and that certainly shows how these cameras have been enabling for doing these kinds of experiments. And they've done a number of other interesting time of flight studies involving the same device. So at this point, let me go through a transition and start to talk a little bit about moving from those airborne LiDAR applications with this technology and how we got into the automotive space. You know, at the point several years ago where we had now been working with folks in the aerospace and defense industry, it was clear that it was the Geiger mode LiDAR was a compelling technology for that application. There were only so many aircraft that could be outfitted with these, and so from a business perspective, it was interesting to look at other markets where Geiger mode LiDAR, and in particular in the shortwave infrared, could have a big impact. And so we began that study and looked at a number of different applications. There are other kinds of robotic platforms, security around various installations. There were any number of different markets, but by far the one that had the largest potential in terms of volume and its impact on this application was automotive LiDAR. And so we began some proof of feasibility work about 5 or 6 years ago in that space. And then within a year of that, it became clear that automotive LiDAR was incredibly hot. You know, you had these sorts of headlines. I think these 3 headlines are all from August of 2016. You had, you know, many hundreds of millions of dollars of investment going into LiDAR companies, valuations for these startup companies that exceeded $1 billion. This transaction that month was actually for a self-driving truck company, but as the headline points out, it wasn't about the trucks, it was about the tech. And the tech, of course, involved software, but the sensors were also a very, very key aspect of what it was going to take for the autonomous vehicle business to get started. And so auto LiDAR was a big focus. So Princeton Lightwave became very interested in raising money to go and pursue that application. As we went through that process, it became clear that an acquisition was a desirable outcome for both us and the people we were talking with. And so in the end, it turned out that Argo was really the best fit for PLI's Geiger mode LiDAR technology. And this is really complementary to the things that Argo has been working on with other LiDARs. And so we're really looking at developing next generation capability to take us out to very long range. So if I look at kind of a very high level comparison of how does the work we were doing for detection for Geiger mode LiDAR for airborne applications and look at, all right, what are the big differences with these automotive deployments? Certainly, there's an enormous difference in range. Most of these airborne applications were at least at quite a few thousand feet, all the way up to as much as, say, 50,000 feet. Automotive, obviously, we don't need that much range. We only need a few hundred meters, although honestly, 200 is still probably not enough for what is going to be needed for highway speeds and all situations. And this number probably needs to go up by at least 50%, probably a factor of 2. But another big challenge is that we really need range all the way down to, say, practically 0. We want to be seeing all around the car. Now, there may be other sensors that can be used to accomplish that, but ideally, if the LiDAR can see at very, very short distances as well, that's very desirable. And I'll point out one of the reasons that's a big challenge. In terms of resolution, I mentioned that Harris was out mapping very large areas at somewhere on the order of 2 to 10 points per square meter. This is sort of a point-to-point spacing on the order of maybe 30, 50, 70 centimeters. That was generally the range they were working at. If we are looking at what do we want for the autonomous vehicle space, looking out at as far as, say, 200 meters, we have a similar requirement. We want, a few tens of centimeter resolution. We would like to be able to see objects that are human-sized, and so it can't be too many tens of centimeters, or we're not going to get enough points on the object that we're trying to image. Now, clearly, cost was a very big factor in the difference between airborne and automotive. The cost of these airborne systems was certainly very high. Defense systems could be easily, $1 million systems. Even the commercially deployed mapping LiDARs might have been somewhat shy of $100,000, but still, many tens of thousands of dollars, and generally between 50 and 100 at minimum. For an automotive deployment, it's clear that it needs to fit into the cost structure of automotive systems. And although initially these are not likely to be, autonomous vehicles are not likely to be consumer products, they're likely to be deployed as fleets. Nevertheless, the cost structure for that entire industry indicates that the LiDARs have to come down to just a few $1,000s, if not just a few $100s. And part of it depends on what they're needed for and what the application is, but clearly there's orders of magnitude difference in cost in these two applications. And then finally, eye safety is obviously a big concern. For automotive, it needs to be eye safe at the aperture. It needs to be able to have a person walk right by the LiDAR on the car and not have any risk of eye safety problems. With these airborne platforms, 1,000 feet was generally the distance assumed to be the minimum to another person, to a human eye. If another aircraft were closer than 1,000 feet to the mapping aircraft, I guess the assumption is there are bigger problems than the eye safety. And of course, don't forget about size, weight, and power, right? I mean, big differences there, and an automotive element has got to be suitable for automotive deployment. So let me just say a few words about one of the big challenges for deploying an automotive LiDAR there's an enormous dynamic range, right? Ideally, you'd like to cover, I mean, like I say, zero, you'd like to be able to see extremely close to the vehicle all the way out to several hundred meters. And so, with a typical laser pulse, probably have 10 trillion photons. That's a calculation at 1.5 microns. It's fairly close to that. Very dim objects could have as low as a 1% diffuse reflection. And at 300 meters, the loss from this 10 trillion photons is just huge. If you're considering a 1 centimeter square aperture coming into your LiDAR, you may only have about 10 photons to work with coming back to the sensor with an object. Black cars are particularly difficult because they can have very, very low reflectance. And so that's one end of the dynamic range. You really starve for signal. On the other hand, you could be imaging very bright objects at very close range. They don't suffer the 1 over r squared losses of diffuse reflections. And so you have big challenges with saturation. And so, I have seen, certainly there are many folks in this community at this conference even very interested in the high dynamic range challenge. There are other challenges dealing with solar background and artificial light sources, in particular other LiDARs is going to be something that anybody working on an automotive LiDAR is going to have to contend with. But it's also an interesting opportunity. And one of those opportunities is, can we take some of those hardware and sensing challenges and solve them with software or really clever algorithmic solutions? And that's something where this community will exceed. And so the photon counting approach is very interesting in this respect because it's inherently statistical. I'll say a little bit about that in just another minute or two. And so there's an opportunity to use algorithms to really solve some of those problems. So just to give you a sense of what we did at Princeton Lightwave with developing a proof of feasibility, we were working with essentially off-the-shelf components. We were using our camera, which was a unique product, but we considered off-the-shelf, and getting off-the-shelf optics. We used both diode lasers and a fiber laser for these integrations, but this case happened to be a fiber laser. And we used a voice coil mirror scanner, which we were able to get off the shelf, and we were able to show really, really nice imagery. I mean, this, it's hard to appreciate how high this quality is for a LiDAR when it starts to look kind of like sort of crummy visible video. and so, you can see artifacts like the saturation from or flare in the optics and other things that can certainly be dealt with in a real product development. But this was very, very encouraging in terms of the results we were getting for deploying Geiger mode LiDAR for this application. And so here's a bit more data. This is right outside what was the Princeton Lightwave facility, now the Argo, New Jersey facility, where we're looking up a 300-meter long driveway towards this highway here. Again, you get a sense of the degree of detail, a truck going by, other sort of details in the buildings around. Very, very good resolution at quite long distance. So in the remaining, 10 minutes or less, what I thought I'd do at this point is just to talk a little bit more now about what we're employing for these automotive LiDARs at Argo and the distinction between this SWIR Geiger mode and the legacy LiDARs that exist today. A lot of what's being used and has been used in the automotive space to date. This is kind of a big summary in one table of those distinctions, the single photon sensitivity versus linear mode, statistical sampling versus using a single shot image of the scene, our work out at these much more eye-safe wavelengths beyond 1400 nanometers versus the use of what has been the predominant wavelength range for automotive LiDAR to date, around 900 nanometers or so. The fact that we're using arrays of lasers and detectors also is a very important factor, and I'll cover that in a moment. And that is in distinction to what has been historically the use of discrete laser detector pairs, which each have to be individually aligned and it poses a challenge for manufacturing. So as you start to think about turning this into a product and how you're going to come up with a manufacturable solution at scale, very large volumes, and at sufficiently low cost, working with arrays, I think is an essential element in the design. The fact that we're working with space filling or gapless imaging is actually a distinction from many other solutions that exist. I'll say a little bit more about that. And finally, the fact that we're doing the design of custom chips, and it gives us quite a lot of flexibility compared to the integration of commodity components. So I'll just run through a few of these, and some of them I'll go rather quickly. You know, we already talked earlier about the distinction between Geiger mode response, where I get macroscopic pulse of current for even just a single photon. What that does is allow me to use the LiDAR energy in a single pulse much more efficiently. I can use the same amount of energy and see further because I can detect returns down as low in energy as a single photon, or I can deploy a system for the same distance using less energy and lower power, lower energy pulses, and that can be very beneficial to deployment. In terms of the fact that we're photon counting, an interesting difference is that as opposed to using one single shot and measuring the analog response at a linear mode detector, we're operating at very high frame rate with these Geiger mode detectors, you know, anywhere from hundreds of kilohertz to even megahertz frame rates. That's sort of the order of magnitude that is relevant here. And what you're doing is a statistical analysis of those time of flight returns mixed in with all of the returned laser pulse energy. You've got ambient photons that are entering the aperture. And so the general approach here is to build up as a function of time, or in this case, range, because time just translates to range, build up the intensity based on how many counts are seen at any given time. So you create very small time buckets enabled by the capability of our imager. That sort of fraction of a nanosecond resolution is what we're working with again. And if there's an object in the scene, what you'll get in this histogram is a significant peak above the ambient intensity background, and you can get the cumulative signal by integrating over this peak. And then using digital signal processing is where there's a lot of interesting work that can go into getting high probability of detection with high confidence in terms of how you analyze these waveforms. The goal is to have enough samples that we can get reasonable contrast. Remember, each photon, each return pulse, I should say, whether it's 1 photon or 100 photons or 10,000 photons, only will give one count. And so what we want is a few hundred of those counts, at least let's say 100 to 200 samples, allows us to do averaging where we'll average both temporally by using those multiple samples, and we can average spatially. We can integrate pixels at a high density, and we can choose to add up the response within a certain area on the array. Of course, that will reduce our spatial resolution, but it allows us to get more signal to do higher probability detection. The shortwave infrared versus near infrared, I've talked about. The eye safety is really the key factor. You know, this shows the maximum permissible exposure to laser energy of different wavelengths. This happens to be the specific case for a point source and just a very short 1 nanosecond pulse. The difference between 900 nanometer safety and 1400 nanometer safety is many orders of magnitude. Now, the details depend a lot on how the system, the LiDAR system, is designed, how the transmitter works. There is not nearly this big an advantage under all cases, but just the fact that we do have this additional eye safety margin allows greater flexibility for how we're designing our LiDARs. And the other thing is, if we need to deploy more energy, we can eye safely, and that may be important, you know, in terms of achieving detection ranges, you know, at 200 meters or more. The shorter wavelengths really start to have a problem with eye safety at that point. Getting to a final point about arrays and space filling, I just want to point out that many legacy applications use a very small laser spot, scan it around, or maybe there are multiple pairs of lasers and detectors, but they're only covering a small area of the resolution element in the scene. And so by the time you're out at 200 meters, even a fairly good tight 2 milliradian resolution winds up resulting in a 40 centimeter cross-range resolution, and you can start to lose small objects. Now, you may not need to see them at that far range, but you clearly want to be able to get returns from everything that might be present within a 40 centimeter by 40 centimeter area. And so, for instance, one way that we've approached gapless imaging, not having those gaps between the points where resolution elements are illuminated, is by using a uniform vertical illumination, a very narrow line with that same sort of 1 milliradian type of divergence in the horizontal direction, but cover the entire vertical field of view with this one beam, and then to use that coupled to an effectively quasi one-dimensional detector array. And so, this just emphasizes the importance of high resolution. This is imagery that was collected with the proof of feasibility system developed at Princeton Lightwave. The data were collected at a 1 milliradian angular resolution to generate this very nice high resolution image. We used the same data and just coarse-grained it to show that what is clearly a human here, well distinguished from trees, starts to be very unclear once you get down to lower resolution. And so this is an example of why we need enough resolution in these systems to be able to discern many objects. One last point that's related is the notion of flash LiDAR. Now, a lot of folks would love to have a solution that has no scanning, but the big challenge with flash LiDAR is that if I want to have high resolution and have it over a wide field of view, I need a very large array. There has been a lot of progress on silicon spads in making megapixel arrays, but even if you have those, then you have to launch a prohibitively large amount of laser energy. So it may be an interesting solution for some shorter range applications, but it becomes very difficult to maintain high resolution when you want to see out at very long range. So we believe that the scanning I just described is really a nice way to balance those needs. And then finally, the last point simply emphasizes that in doing our own custom development down to the key semiconductor chips, it gives us a lot of flexibility in how we influence the behavior and the performance of the higher level system. And in particular, that Geiger mode APD detector array is critical. Another technology that we do have internally at Argo that came with Princeton Lightwave was a laser diode, a complementary laser diode array technology at these wavelengths, and something that allows us to create solutions that are very low current with still having high power output that's much more suitable for an automotive environment. And so this is a summary again of those elements of the Argo LiDAR approach: single photon sensitivity, the eye-safe wavelength range, using single chips, monolithic arrays of a significant number of lasers and detectors to get a much more manufacturable solution where we just have a single alignment of the laser diode array to the detector array. And then it gives us gapless imaging because of the way we can illuminate everything across the entire vertical field of view. And finally, the benefit of the custom chip design. And so, as many of you are probably aware, there's an enormous amount of excitement about automotive LiDAR in terms of the number of companies that have started pursuing this technology. Depending on whose estimate you take, there are probably anywhere from 80 to 100 LiDAR companies today. At least at this point, I believe that Argo is still the only auto LiDAR developer that's working with Geiger mode technology at the eye-safe wavelengths beyond 1400 nanometers. Geiger mode is being adopted in silicon for shorter wavelength use, and there are companies that are looking at using longer wavelengths like 1.5 microns for eye safety, but I believe we're still the only organization that is combining these two in our solution. And so to sum up, we looked at some of the ways in which that Geiger mode LiDAR technology had been very effective on airborne platforms. The development of that shortwave infrared Geiger mode camera was a key enabler for many very high precision timing, time of flight imagers and the applications that we took a look at. And that's transitioning now to automotive deployment, which I and all my colleagues are very excited about. And let me just finish with the thought that there are probably very significant opportunities in this space for the computational imaging community. We talked a little bit about the high dynamic range challenges. Imaging in difficult environments is going to be a reality of autonomous vehicle deployment. Fog, snow, other dispersive media types of situations, smoke. These are problems that we're going to need solutions for, and you guys are absolutely the community that can solve them. The mitigation of environmental noise, solar background on bright sunny days, other LiDARs, other artificial sources, even the application of non-line of sight imaging to the automotive space. And then finally, how do you maximize the amount of information that can be extracted from this approach we're using with counting single photons? So just to finish up, let me thank the incredible team of people that I've worked with for more than a decade, folks, both my former colleagues at Princeton Lightwave and my current colleagues at Argo AI. There's been a tremendous amount of effort from all of them, and I'm very thankful to have worked with them. And thank you for your attention.
Fantastic. Thank you so much, Mark. Okay, so I guess we're in the Q&A session right now, and I already see a whole bunch of questions in the chat. So thanks again for the great talk. While the questions are coming in, let me just start out with a quick question on my own. So we've recently seen that Apple has released like this mini LiDAR in the iPad Pro line of products, and it's kind of, expected to be a major platform now also for mobile devices. Now you've talked about the one extreme from, kilometer range scanning in airborne systems to, a couple hundreds of meters in automotive. Do you have any thoughts on like these mobile applications and how that may be different? Or could you maybe speculate even what is an ideal platform and for this kind of a system? And, what should we think about in that context? Is this silicon? And, lots of questions around that, I guess, but.
Sure, absolutely. And what I would say is, the fact that there are so many companies out there with interesting technology to try and solve this problem is really partly because there's not going to be just one solution. I believe that with three-dimensional time-of-flight imaging, there are so many different ways to tackle the problem that certain solutions are going to work better in other cases. And so, yeah, for mobile platforms, in terms of cost, in terms of size, weight, and power, the old adage that if you can do it in silicon, don't bother trying to do it with anything else. I think that's absolutely going to be the case there. And the deployment of silicon SPADs in those same platforms has really been exciting over the last several years. For proximity sensing and autofocusing, there are many hundreds of millions of SPADs that have shipped, in silicon platforms for various products. And so that's something that, yeah, I absolutely see that going into mobile devices. And I would say that is going to be a silicon-based solution.
Fantastic, thank you. So I'm going to start with a couple of the questions from the audience here. So Josh is asking, if you had one dimension to choose for which you would like to see improvements in the automotive LiDAR space, let's say if this is dead time or time resolution or bandwidth or more pixels or, whatever you come up with, what's the single dimension where, you would like to see improvements?
Well, of course, the requirements never come in one dimension. They want all of it at the same time. Fair question. I think certainly from the perspective of our team, we're focused on range, right? We really want to get to longer range than people can see today with high resolution. So, I mean, to be fair, you do have to kind of combine those two dimensions. When you talk about range, there are lots of other things you would wind up trading off. But I would say that we want to see, let's say, longer range than we do today with at least the same resolution that we have now. And that's because we want cars to be able to go up to higher velocities than they've gone, and to get more information more quickly, give the software system more time to make the decisions it needs to make.
Okay, great. So then George has a question, and he said this is a great talk, and he has two quick questions. One is like, how do you deal with the interference between multiple LiDARs operating at the same wavelength?
Yeah, so that's certainly another very important problem. Something that imagine in the RF domain, you have similar solutions based on coding. I certainly believe going to be a coding based type solution, as well as understanding how much disruption in your signal can you tolerate from other LiDARs. And so part of it is a software solution, but on the hardware side, we need to do our part with coding.
Got it. And then he has a second question on, he thinks that the bandwidth requirement are pretty enormous, because you're counting individual photons at like millions of times per second, right? So, are there big computational challenges, or is there a trade-off between algorithm complexity and, frame rates that you can achieve?
Yeah, certainly that does become a consideration. Folks who take a look at this problem and think about taking the raw data off of the sensor are faced with a big challenge on how big that pipe needs to be. And so this is definitely one of those cases of doing a bit more of your processing at the edge, working on this, at the sensor, to at least do some of those first statistical steps on histogramming and generating the 3D point clouds that are going to come off of the sensor itself. I can see a point at which we want to go take all that data and take the raw data off, because I think there are probably a lot of things you can do with it that we're not doing today. But at least today, generating the 3D imagery is something we can do on the platform. And of course, it's at a much lower, let's say, resolution than the number of points we're getting for pure single photon detections. Okay,
got it. So Atul has a question on using these sphere spats. He's saying that they may exhibit worse dark count and after pulsing properties, and maybe also longer dead times than silicon spats. Are those not drawbacks for automotive as well? Can you maybe comment on this difference a little bit more?
Yeah, no, Atul is right. It certainly makes our lives more difficult. and so, that comes back to the point I made earlier, that if you can solve the problem with silicon, awesome. It usually has better performance than most other material systems if it's within its range of capability. But what we find is that whereas, yes, the dark count rates are higher in these materials because their band gaps are smaller and thermal effects are larger, in fact, dark count rate is kind of a non-issue. We've done the scaling up to the kinds of operating temperatures that we need to be at for an automobile. And as it turns out, it's the solar background can often be larger than the dark count rate. And so you've got to find a way to deal with that noise anyway, which we have. And so the dark count rate is really not a big inhibitor at this point. I'd love it to be better. It would give us more flexibility, but it's certainly good enough for where we are today. His point about the dead time is an interesting one, and that also, you'd love to be better. What he's referring to is the fact that once a detector fires, you have to wait a certain amount of time to rearm it, or it's very likely to fire again as a dark count, and the so-called after pulsing effect. And that's something where, we've pushed the rearming down to microsecond. And I would love that to get better, but again, it's a limitation that we work with today, and it doesn't pose any problems for realizing the performance that we need from the system. As that gets better over time, as the material properties improve, we'll be able to utilize better detectors with that property.
Sure. Okay, so Atul also had a second question on this distinction between Geiger mode and linear mode APDs. Is that a binary distinction, or could this be a spectrum? Could you just operate a linear APD at a higher voltage and just operate it as a SPAD, or is there more to it?
Yeah, that's also a very interesting question. There's been a lot of work over, in fact, many decades about, is there a sub-Geiger mode? What I'd say is it really depends on the material system. Nothing I've seen, certainly in the indium phosphide-based detectors and even in the silicon detectors, the nature of the avalanche breakdown really allow you to get to gains of, say, many thousands, but not a total runaway of the avalanche. The one material system that I'm familiar with that does allow you to do that is mercury cadmium telluride. Those are longer wavelength, usually used for longer wavelength detectors, although they can actually detect in the sphere. They have an interesting property in that they never actually go into a runaway avalanche. And it's difficult to make them work up at gains of 1,000 or a few thousands, but there are a handful of companies that have, basically defense companies. Problem is that it's an extremely expensive technology. It's been around for many decades. It's not clear that it can scale to the kinds of applications that we're tackling with silicon or the compound semiconductors, the 3-5 semiconductors. So while it exists, I don't believe there's a material system out there today that will allow you to do that well with something that's deployable.
Okay, but you can't just crank up the voltage on any detector and turn it into a SPAD that way, right?
Well, you when you go past the breakdown voltage, yeah, you get a SPAD, but to try and get an analog linear mode gain of an equivalent amount of thousands, something that allows you to basically get down to the single photon level, that's not, I'm aware folks can really do in a deployable way.
Okay. So Chris has a question, and he's asking if you could maybe comment a little bit on the relative strengths and weaknesses of Geiger mode versus FMCW-based LiDARs, because that's something we've seen recently emerging, at least in research papers.
Sure. I mean, the instantaneous velocity capability of FMCW is very compelling. It's a really interesting capability. Of course, most of the automotive manufacturers today are using radar to get similar kinds of data, but the coherent detection, with light is going to give you much better resolution. I think there are challenges in terms of collecting sufficient data for high resolution over wide fields of view with FMCW. Can it be scanned quickly enough? Our ability to deploy reasonable size arrays and do the Geiger mode detection over a large number of detectors, kind of parallelizing the measurement quite dramatically is something that, whether it's the SWIR or the silicon SPADs, I think is very compelling for the imaging. And so it is quite possible that those two emerge again as complementary modalities in autonomous vehicles. And I think, FMCW is just sort of at its early stages. It'll be very interesting to see where that goes as it matures.
Okay. There's a few more quick questions. Akshat is wondering if Geiger mode LiDARs have any advantages over standard LiDARs in terms of the dynamic range.
They certainly have an advantage on the low end in that we can get down to single photons.
Yeah.
With the linear mode LiDAR, again, it depends on which detectors, material system you're working in, but generally hundreds of photons are needed, at least tens of photons, even if you're working with silicon. So on the low end of the dynamic range, the Geiger mode does bring you an advantage. At the high end, the question is, how well can you deal with saturation in those two systems? And there, I think, wind up with similar problems in many respects. And the fact that the Geiger mode number resolving means we're going to use sampling approaches in terms of trying to get large contrast. But from that perspective, I say it is harder to get large contrast from a Geiger mode APD because it requires making that many more measurements in order to build up enough bits of dynamic range.
Oh, okay, okay. Let me ask one more question. Can you maybe speak about the strategies that automotive LiDAR companies use to deal with interference from fog, snow, and other weather conditions today? Is that a big challenge, or?
Yeah, I mean, I think part of the challenge is, in fact, the characterization of the performance of the systems in those environments, and so testing is certainly one big factor. And we're looking for better performance in those cases. I don't think I can speak to the very specifics of what is being employed to try and approach those most difficult scenarios. What I would say is that on a very pragmatic level, it's going to limit to some extent where you roll out your systems first, and you are going to work in environments that are somewhat more forgiving in that respect. It's going to be longer before you find these cars deployed in cities where there's fog all the time, or enormous amount of snow, or that sort of thing. So I think that's a long-term problem to solve, and I think the entire computational imaging community is tackling that, and I think that the automotive players are going to adopt the kinds of solutions that come out of that work.
Great. Yeah, I have a few more questions. I'm not sure how to mention. Yeah, so maybe Mark can stay online on the chat a little bit for a couple more minutes and answer a few more questions there. So thanks so much for joining us today. And thanks for all the questions on the chat. This was really exciting because we've really learned how to not only, leverage some of these emerging single photon avalanche diodes for different applications, but I mean, many of us work on computational challenges. So I especially appreciate that you commented a little bit on, some of the open problems and where we could help. I think one of the things that seems clear is if you really want to deploy something, there are certain constraints on the bandwidth and so on, and making it work on some kind of a mobile platform, seems very important.
Absolutely.
So thanks a lot for joining us, and yeah, we will stay on the chat and answer any further questions that people may have.